Hi, everyone, and welcome to March's virtual lecture. My name is Carla Gonzalez, and I'd like to introduce you to our speaker today, Thomas Campagne, who is going to be demonstrating how to apply an isostatic correction to gravity data through a case study over central Chile using Geoscience ANALYST Pro Geophysics. If you have any questions during the presentation, please don't hesitate to type them into the Q&A. And just a quick reminder that this webinar is being recorded, and the recording will be on our YouTube channel in the coming days. So without further ado, go for it, Thomas.
Yeah, thank you, Carla. Thanks everyone for joining us today. As Carla just announced, we'll be looking into how we can implement gravity bouquet and isostatic corrections in Geoscience ANALYST Pro Geophysics and the VPMG software that's provided with it. It will be an application of this correction to satellite and ground gravity data. The isostatic correction, for those of you that are familiar with it, will be based on the ARI ice cannon model, which assumes a lighter crust, Earth crust, that floats above a denser mantle, and that crust has a variable thickness, but has a constant density. So the bouquet and isostatic corrections in this example today will be computed through forward modeling of crust scale 3D geological model that we're going to build from public data in Geoscience ANALYST. So let's get to Geoscience ANALYST here. So in Geoscience ANALYST here, I've already compiled all the data necessary for today's presentation, and I'll walk you through these nested data grids here on the screen. So the larger grid here is the eTopo global bathymetry and topography model. Then the next smaller grid here is the world gravity map data from the Bureau Géophysique International. So we've got the free air data here that is displayed right now, and this model is based on satellite gravity data and is computed onto the eTopo bathymetry and topography model. Then the smaller grid here is the NASA DEM, which is an updated version of the SRTM DEM. It has a higher resolution here, and so it captures more detail of the topography than the eTopo model that we've got around here. And then here in the center, we've got these little spheres here represented the gravity station compilation that was done in 1993 by the USGS in South America. So we're in central Chile here. So the last data set that we haven't actually discussed here is, I'm going to hide everything, is the GEMMA grid. So the GEMMA grid is a crust depth model that has been computed globally based on the Goche satellite gravity data. So here, the grid that's actually displayed here shows us the depth of the crust in kilometers. So as we're in GA, I've used for each of these data sets quite a convenient feature here. Each time I click on one of these folders in the object tree, you can see here I've got some files attached to it. I've got the PDF of the paper related to that grid, and I've got also a web link. So if I actually select, let's say, a world gravity map, I click on it, and this will bring me an actual website of the data set. So it's also a good container of information, so to keep track of where things are from. So it's something to keep in mind. So now that we've went through the data, we're going to start to build our geological model at a core scale, at a 10-kilometer scale. So first of all, we'll focus on that crust model here. Right now, it's just a grid sitting in space, and we'll extract a surface from it. So the first step that we want to do is to convert the crustal depth in kilometers to meters, to do that, I will apply a script, and that script will be crust bottom in kilometers times 1,000, and the output property here will just be crust bottom in meters. So you can see here we've got the name of the property is showing in bold here, which means that it's actually found on our grid. So it's a good way to kind of like cross-check that there is no typo into the script. So I apply. I know I've got my converted grid here. And now I will extract a surface from that grid. So I'll right-click on the grid and I'll create a surface from data. And I will name this surface GEMMA crust bottom surface, and I'll use the metric property. All right. And now we have our first surface for model. We've got the MOHO discontinuity here in 3D. So we can see we've got a thickening of the crust here where the Andes are located, and we've got the oceanic crust here quite flat. All right, so the next step now for us is going to be to build our 10-kilometer resolution model. So for this, I will use the same extent as the topography, the eTopo grid here, and I'll build a 2D grid from that. So I'll use the 2D grid designer. I will select by picking this object here, and I'll use the light bulb to actually extract the origin, the grid size, and the cell size of that existing grid. And then from 4-kilometer cell size, I will just increase this to 10 kilometers. Once this is done, I can just give that topo, that new 2D grid a name. I'll call it regional 10-kilometer grid, and I will just create the grid. So you can see I've got a new grid object that appeared here on the left at the base of the object tree. That grid doesn't have any property on it. So what we want to do now is to transfer a property onto that. So I'll go into utilities, transfer data, and I'll transfer from our topography grid here. I will select the eTopo data, and I will transfer that onto that regional 10-kilometer grid. So now it's a kind downsampling our topography. So we've done that. Now to keep building our model, I will need to actually create two surfaces from that model. One that represents the surface of the Earth, so that would be the surface of the ocean and the topography, and another one that represents the bathymetry, and this will be used to actually represent the volume of water, oceanic water here to the west. To do so, I will apply a script on this property to actually remove all the elevations or set the elevations at sea at the 0 elevation. So I will create a new property. That's called eTopo no bathy. And I'll use a conditional script here that I've saved on the side that's looking at all the values of eTopo that are below 0. If that's true, I set them at 0. If it's above 0, I keep the topography value. All right, so I created my new property now. I just want to set the color range to the same one as before. There we go, and I'll just select the elevation color scale. So now we can see just my two properties here. And I will create, as we've done before for the GEMMA crust model, I will create two surfaces here from this grid. So the first one will be the regional topography surface. And that would be the topo without the bathymetry. And I will create the regional bathymetry surface, which is just the topo one. All right, so now if I just remove the grid, we've got all the surfaces here that will help us build the 3D geological model that we can evaluate with VPMG. So from these surfaces that I will just momentarily hide, and I'll bring our original grid here, I will use this grid now to define the extents and the resolution of our VPMG model. We will need to create a VPMG model or VPMG mesh in order to compute the geophysical response of that model. For this, I'll go into utility, and I'll select VPmodel designer. Here, I will select the grid, and I pick the same origin, model size, and cell size. I'll select the topography as the original topography surface here. The default base of the model is -25K, but in our case here with like crustal scale modeling, we want to increase that at a -100 kilometers. And I want to add 2 more surfaces to the model, the base of the crust and the bathymetry. And I will name this model regional crust model. Now create. There we go. So we can close that. So if I remove my 10-kilometer grid, I've got a new object here that appeared where I've got a unit property, which is a discrete property. And for each class, it represents a geological group. We've got a physical property associated to it that's not yet defined. So we're gonna look into that. So here in the data colors for that object, I will rename this unit crust for clarity, give it kind of a brown color. There we go. This unit here will be the water, and let's keep the water blue. And here, that VP basement, we'll call that mantle. And I'll put that in green. Here we go. For the property, let's call that property an actual density. And I will call that density CBG for complete booging. And you'll see why, how we're going to set that property up. I will also create a second property here, density iso, that will be used for the isostatic direction. There we go. And we want the density of the crust to be set at 2.67 grams per cc. Same for the other property. The seawater will be set at 0.27 grams per cc. And here, we don't want, for the complete Bouguer correction, we don't want any contrast between the base of the crust and the mantle. We just assume a constant density below topography. So in that case, we'll set the mantle here at 2.67. And when considering the isostatic correction, we want a density contrast at the base of the crust. So that mantle will be set at 3.27 grams per cc. So now we have a model that where every single cell has a geological ID attached to it and a physical property. So our model is ready. We just need now to create the data locations on which we'll compute the response of this model. So now we'll actually look at our gravity data here. So I'll just hide the model for now. And I will resample our gravity data here at 10 kilometers as well. So I'll use the 3D grid designer again. I'll select the object here. And I'll change the cell size at 10 kilometers. And I will name that new grid 10-kilometer grid. There we go. And I'll put that here. And that grid doesn't have any property yet. So what we want to do now is to actually add data to it. So I'll just transfer all the gravity data sitting on the higher resolution grid onto this new grid I just created. So now I've got the free air at a 10 km resolution. And to do that, now I need to extract the points from that grid and locate them in 3D. So I will just create first a surface that will represent the topography, because that's the true actual 3D location of this data. And I will name this surface here, eTopo surface for clarity. Here we go. Then I'll do the same thing and extract my free air data, which initially will be located at a wrong elevation set by the free air data, but that's not, that won't be an issue for long. All right, so now I've got these two surfaces here. One contains the free air data and the other one contains the topography. So now I will actually just drape my free air surface onto the topography. So that surface that contains the free air data is now draped on topography. So this free air data are properly located on topography. And I will then finish this by extracting the points. From that surface. So it's kind of a little multi-step process to extract the nodes here, but we pretty much have our data now. One last thing that needs to be done is to actually remove all the offshore points here that we don't want to use. And to do that, I will just display the elevation. And when selecting the property here, I can actually only display the points that are located under 0. There we go. I will choose to edit the point set. And with a shift, click and drag, I will just select all these points. So I only selected the points below 0, only the displayed points here. And with Control Delete, I will just delete these points, escape the edit button. And if I displayed again all the points, I only keep the points that are located above topography. So now we have our data points, we have our model that I will display here. So the next step here will be to actually compute the response of the model into this data. And I'll go to Geophysics, compute forward model. I'll select the gravity type. My observation points are here, for data. I will select the 3D model here, regional crust model. We'll start with the complete Bouguer correction. The surrounding half space here will be set at a constant elevation of 0 meters. And I will name the output here, regional CBG for complete Bouguer correction. Click on apply, which will kick off the forward modeling process. And now in the object tree, I can see I've got two new properties that appeared on our data points. One is the computed response, so that would be equivalent to the complete Bouguer correction, and then the residual, which is the calculated response minus the observed data, which in our case would be the complete Bouguer anomaly. We'll do that for the isostatic data as well. Here we go. Just keep that aside. And now if we look at a top view, so we've got our free air data. We got the complete Bouguer correction and the complete Bouguer corrected data here. Then we've got the isostatic and terrain correction combined together. So that's the response of the model. And now here we've got the isostatic residual, which is the isostatic anomaly data. So here we worked at a very large scale. How can we apply that to a finer level and better define the resolution of these corrections and better define the topography as well? So if we want to actually consider now our ground gravity stations here, we can add actually a finer resolution model that will better capture the topography and use that to actually compute the isostatic and complete Bouguer correction on this data again. So to do that, I will generate a new 2D grid. And here on the top view, I will just drag something around my data here. A little bit bigger. There we go. The cell size, I will put that at 2 kilometers. There we go. Perfect. And I will name that grid local 2 kilometer grid. Perfect. It's a grid that has no property yet, so we'll transfer 2 properties on it. We'll transfer first the etopo, because we want the bathymetry. All right. And then we'll transfer the actual NESA DEM. That's the higher resolution DEM that we want to use here. Perfect. And now I want to compute one more surface where I want to keep the resolution of the NESA DEM onshore, but I will need the bathymetry as well. So I will combine these 2 properties where we've got the etopo bathymetry and the NESA DEM together. And I will do that using a script. And that script, I will create a new property here named NESA DEM with etopo bathymetry. And it's a conditional script as we've used previously, where we keep the etopo below 0 and we get the NESA DEM above 0. There we go. Perfect. So now we've got the NESA DEM here, the etopo over here. And I did that because in this model, I want to keep the volume of water located into the north west quarter here. Then I want to add one more thing to that model, which is a model base at 10 kilometers. And I'll just name that base, and I'll give it a constant value of 10,000. All right, I'll create surfaces from these grids. There we go. And I will create the local topography surface first, based on the NESA DEM. Then the bathymetry, based on our combined properties. And did I create the surface? No, so I'll just repeat that here. Bathymetry, go. Perfect. And the base surface. Perfect. So now I've got these 3 surfaces here that will be used to generate our model. And now I'll generate that VPMG mesh with the VPmodel designer. I'll select this grid here to get the same 2 kilometer resolution. The topography will be our local topo surface. Model base at -25K, that's okay in this case, and you'll see why. I'll use the local bathymetry and the local base. And I'll give that, that name local crust model. Perfect. So now I've just removed the grid and the surfaces, and we've got our local crust model here. That's kind of like nested as a higher resolution. And here too, we want to keep that as the crust. The local bathymetry here, that's water. And that's below the model. And that will be actually ignored here. The crust will be at 2 0.67. The water as before, it doesn't change, 0.27. And below 2.67, just so it has a value. So now what we're going to do is that we're going to actually incise this higher resolution model into our regional model. So we'll capture the long wavelength components of the signal from everything that's surrounding our local model, from on either side and from underneath the model. So we'll capture the MOHO geometry underneath the local model area as well. So when I'm computing a forward model, I'm just bringing back the window here. We'll be using our stations here with the free air anomaly here. Our model will be our local model with the property that we've just set here. Our regional model will be the larger model, so density complete Bouguer. And I'll use the incision method that's removing. So it's just removing anything that's underneath the local model. It will be attributed with the regional model geometry. And no, I will call that local CVG. And I'll run the forward modeling here. So I'll take a few more seconds because first the regional model effects onto the local model data is being computed. And once this is done, it computes the local response of the model here. So we're almost there. There we go. And then I'll do it for the isostatic correction as well. And these data are being computed onto our ground gravity stations here. So we'll see the results on these points. Some suspenseful seconds here while the forward modeling is taking place, and we'll be almost done for this demonstration. There we go. Perfect. So bring that on the side now, looking at a top view. So now on my local model area, I better captured the topography, so I'm able to better evaluate the corrections for the terrain correction and the complete Bouguer and the isostatic correction. So that would be the Bouguer correction. And here it's the complete Bouguer anomaly that we're looking at. And here there would be the combined terrain and isostatic correction. And here we're looking at the isostatic residual. If I want to better visualize this data, I can also just choose to grid this on my local 2-kilometer grid. I can select my source object here. Only select free air. There we go. And at 50K, it should be enough. There we go. So now if we look at what's sitting on our local 2-kilometer grid, we've got the free air data, the complete Bouguer corrected data, and the isostatic corrected data here on a more of a grid form. So I hope this has been useful to you all that have attended today, and I'll be happy to answer any questions if that arise. Thank you.
Great, thank you, Thomas. And thank you to anyone who joined us today. For those who are here live, feel free to type any questions that you may have, or feel free to raise your hand as well. I'll note right now that if you have any questions in the future, please send us a message to support@geoscience.com. I would be happy to answer any further questions you have. Okay, so I don't see anything yet, but we'll just wait a couple seconds.
I can see a hand was raised here.
Oh. Oh, all right. Let's allow it to talk. Did I do that correctly?
Oh, hey, I think I'm unmuted. Am I unmuted?
Hi, welcome.
Hey, Thomas, it's Joel.
Hi, Joel.
Hey, very good. Look, I want to thank you for that. It's I'll admit I'm going to have to go through it again to right to really follow through. But it's actually something that I've been looking forward to for a long time. So I just want to say thanks for that. If I had a question, when you chose I guess basically the density of the upper mantle, I think you took 3.27. Was that a number that you kind of pulled out of the hat? I actually went and did a quick Google, and it suggested something like 3.9. So I'm just wondering where that came from.
Yeah, what I did is actually, since I was working with the world gravity map data, I used the same density contrast that they used in the paper. So
Okay.
for that model, so for seawater was 1.027 and 3.27 for the mantle density. Yeah. It was just for that example.
And then I know that this isn't really a GA tutorial, but how do you attach? I didn't really know before this that you could attach a file and a web link to a grid like you did at the start. Is that just a drag and drop into the?
Yeah. It's just a drag and drop. Like this is one of the best features that I like, because you can actually carry, the PDF report with your survey or drilling logs, or so you've got that field files here on the not on the objects, but on the folders in the object tree. And for each folder, you can drag pictures. Like this is a, when you save a URL website link on a folder, you just drag and drop it in there, and yeah, it sits there. It's embedded in the GA workspace, and then you can open the PDF or use the link.
Great, thank you again.
Yeah, you're welcome.
Great, and I see that we have a couple other raised hands, Toma. I don't know if we want to go ahead and do that. Great. So John, I believe you're up, but you're muted. He's still muted. Asked to unmute. Still muted. We have another question in the meantime. We can go ahead with that one maybe.
Hi. Thanks very much.
Hi.
So I'm pretty new to this, but I was just wondering if it's possible to increase the resolution of, let's say, a crustal thickness model using higher resolution data. I know you use the global models in order to derive the crustal thickness or the base of the crust, but can you integrate higher resolution data to refine that?
Yeah, exactly. You can. It's all based on the the resolution of the model that you're doing, and also if you got a finer, or a more accurate or finer resolution crustal depth model. As far as you have it in a grid form, you can bring it into GA and combine that higher resolution data with maybe surrounding lower resolution model, a little bit like I've done in to recombine the bathymetry and topography together. And then once you have that, you just extract the surface, and you have a surface that contain the higher resolution data where available, and then follows with the lower resolution model around it.
Do you have any examples of where this has been done in purely oceanic crust or arc crust rather than continental arc?
No. I've been more focused through my work onto onshore or continental mining exploration. So most of the examples of the things that I've done were not located offshore.
Okay. Thanks very much.
But I don't see how it cannot be done.
Yeah, I hope so. That's kind of what I was thinking of. But yeah, no, that's great. That's awesome. Thanks.
You're welcome.
Great. We have two more. In calculating the CBG, was the elevation from the points or the elevation model?
Well, the points for the satellite gravity data were evaluated, like the free air data were computed on topography. So the elevation of these points was relocated on topography. That's why we draped our free air data on the topography. So that's where the complete Bouguer correction and the isostatic correction were evaluated.
Great. Just one more so far.
Okay.
So can you confirm what observation height the free air WGM data is at?
So for the documentation that's provided with the models and I mean the papers and scientific articles, all their gravity data for the world gravity map have been evaluated on the eTopo model, so that bathymetry and global topography model. So that's why I chose that model, because a lot of like satellite gravity models are being evaluated on the geoid surface, which is the 0 matter orthometric elevation, which is of no use for like mineral exploration, I would say, because you really need to you cannot directly use this data.
Okay, great.
All right.
It seems like that's it. I'll just remind people that this will be on YouTube in the next few days and also on our LinkedIn page, since this is the first time that we did a LinkedIn live event. And we'll also see you next month when Jem Mitchell will build a greenfields exploration project from public data in Geoscience ANALYST Pro. And do note that this event will take place at 11 a.m. Australian Western Time. So depending on what side of the world you're in, we will either see you live or make sure to catch the recording on YouTube shortly afterwards. And that's it. Thank you, everyone.
Thanks, everyone. Bye.